Good morning, good afternoon, or good evening, everyone. Depends on where you are. And this is Jeff. I'm the product manager of Crystal Instruments. And as you know, we just announced EDM model software. Okay, so today I'm going to show you the complete operation of the EDM model software. And if you can see my screen, and this is a new test wizard for this. Compared to before, we have DSA and VCS. Now we added a whole new category model. Excuse me, if anyone can mute his microphone, it will help for the audio. Okay, thanks. So for the model, so far we have implemented 3 test types: input FIF, hammer impact, and MIMO FIF. For each of these, they include the model analysis feature. But the first one, input FIF, it's just assume you've done the model testing to acquire FIF signals. So you have the FIF signal ready, so you can just input and perform the model analysis. The second one, hammer impact test, we integrate the hammer impact model testing with the model analysis. So it's a complete package in one. While for the MIMO FIF, it actually includes the IMO model testing and also MIMO model testing using the model shaker or model shakers. Depends on your setup. So these are 3 types. So these are the 3 testing types. Okay. I still hear some microphone feedback, so if anyone has not muted their microphone, can you please check? Okay, so let's continue. We have 3 test types, as I mentioned. So, and let's move on to look at the hammer impact test and also the MIMO FIF test. And as Brady mentioned at the beginning, this EDM model is a complete model testing and analysis software suite. So now we integrated testing and post-analysis into one. So that's an obvious difference, or say enhancement, compared to say before we work with any scope or any other software. So you do it like into separate software and you run in 2 steps. Okay, let's move on to look at the hammer impact testing. So I believe if majority of you already run the EDM software, so you will see very familiar the GUI and the setup of this EDM software, no matter you run DSA or VCS before. So here, this is the EDM model hammer impact testing setup. So on the left side, you still have this test list and also the signal list, the display. But with this model software, you can see we added specific tabs for different stages of the testing and the analysis. So we will go through this and show you how they function. So the first one is the geometry editor. As Brady mentioned, the first option for EDM model is called EMA-01, which includes the geometry editor, animation, more specifically, motion animation, and ODS, operation deflection shift. So that includes in the first option, the EMA-01. So the geometry editor just helps you to create any kind of geometry you are going to testing. So the idea is very straightforward. So you can create the components of the structure by point, line, or surface. You can add all these graphically or through this table. So the table just manage this. Say the first level is the component. So if you are dealing with a complicated structure, you can cut into multiple components. You can say the base is a plate, in the middle you have a cylinder, on the top you may have a sphere. So you can build this structure using multiple components. And within each component, you can define points, and you connect points, you get line. You connect 3 points, you get a surface. So that's the way we build up our structure. And as I mentioned, you can do it graphically or using this edit table. But to make it more efficient, we added this component library, like a beam component. So you can add a line. You can specify the starting point, end point, and how many sections you want to cut into this beam structure. So by doing that, you click OK. Let's just do it. So you can see a line has been added. So that's a beam structure, or say component being added. And if you say, oops, I made a mistake, so you can go back just to remove the previous operation. Or if you say, I deleted something by accident, you can redo it to bring it back. So, and let me just also quickly show you, say, this at the panel. So this is a plate. So you can define its geometry, say the width and the height. Of course, first you start saying which plane you want to go into. So it's sitting in the XY plane, so the perpendicular is the Z direction. So you can specify all these. And then you can say, I want to cut into how many sections. Also, if your plate is not straight, you can rotate it. So you can say rotate it by 20 degrees along the Z axis, or say XY plane. So you can have any way to define this component. I will call it, this is a component of the plate. And of course, for every point, you can define their local angle. You can rotate it to any axis. So in case your structure is not like a flat. Okay, so that. Excuse me, I hear some voice. Can you please just mute your microphone? So today we have a relatively big group. So yeah, thanks. Okay, so here, and of course we support several format input. At this moment, we fully support the UFF format input. So you have a file defined the point and the lines from the UFF file. You can import it. So you can use this to import that. And we're also going to support the CAD file and FEA model input, but we will do some further processing to decimate the points down to acceptable level for model testing purpose. I think you are aware for FEA or for CAD model, you may have thousands or even tens of thousands points. That's not practical for model testing. For model testing, you're handling with dozens of points, or I would say 100 points. That could be kind of pretty complicated structure. So we would support all these type of geometry input, so that will help us to do that. And also you can save the structure to an XML file, and it can be recorded by other test type if you don't want to build the model again. And if you say you make mistake, you can just say clear the model, and you can just remove it. But as I showed you, I can recreate this plate simply in a few enter values and just say I click it. Okay, so that's how you build your geometry model. And of course, for the display, we have supported features, rotation. This is like a well-controlled rotation along any axis. And this is, you can pan the model to anywhere. Of course, zone in, zone out, straightforward. If you rotate it or move any way around, you can just say reset to bring it back. And also we support the perspective view and the quad view. With the quad view, we show the top, front, and the side view of your geometry model. And this also can be used for animation. When you do the animation, you can do the very similar thing. Okay, let me bring it back to here. And for the display, you can turn on the point or you can turn it off. And you can turn on the direction for each point. And if for every point, you can change its local angle. And people call it Euler angle. So if it's tilted, you can just define, say it rotates around the z-axis for 10 degrees or 15 degrees, whatever. But you need to specify them. So then the vibration measurement will be assigned to your local coordinate system. And also, I forgot to mention at the beginning, we support Cartesian coordinate system, cylindrical coordinate system, and also spherical coordinate system. So all these three can be combined to build a really comprehensive geometry model for your testing. Okay, so let's move on just to quickly check some display features so we can show also the points so associated with that. And also for the line, we can show or hide. And for the model, we can just show the line without the surface. So we can show also the surface and also the surface knob. The surface knob depends on how you connect these lines. So if you manually create, I would suggest you follow the same convention. It follows the right-hand rule for the direction of your surface. So when you do the animation, you can turn this knob direction to the surface on so you can see how it moves clearly. Okay, so I think that concludes the geometry editor. And here's the one last feature here. You can save this graph display to a PNG file or JPEG file. So that's a small add-on. Okay, now let's move on to look at the hammer impact testing setup. So now we have this integrated setup, this input channel setup. It's very familiar, or say very similar to the DSA or any kind of test. And before we go into these details of the input channel setup, I want to mention the setup test configuration briefly. Since this is a hammer impact test, so you have the choices, say, the roving mode selection. So you can either say I'm roving my hammer or I'm roving my response, the measurement point or points. So for this case, I stay on with the response because I'm having like multiple transducers, and so it will be more efficient if I roving the response. So it will increase the efficiency. But more often people will say, hey, I want to roving the hammer because it's easy to go through and I don't have too many points to measure on my structure. So you can do that. Just select roving excitation. And auto increment, you can turn it on or don't turn it on. So if you don't turn it on, after you finish a point, you can click the next point on the control panel. We will show that later. So, and the idea is to go through all your points on your structure you defined. So first you have this mesh structure defined, and then your testing will follow this pattern to cover all the points, to get all the transfer functions for each point. Auto save, it's straightforward, or prompt to save. One very common feature for hammer impact test is called double hit detection. We implemented this so you can enable double hit detection, or you can say auto reject. So whenever the double hit detection detects the double hit, it will reject that impact. So it will ask you to do one more impact again. So that's very useful features, and I can turn it on just to illustrate this while I do the hammer. I think I can on purpose to get a double hit. Okay, so that's the setup. And the FFT setup is very same as that for general DSA. So you can select your frequency range, block size. And for hammer impact test, I would recommend you tune the block size so that the response can decay at the end of this block. If this is achievable, then you don't need to use the window because you won't encounter any leakage issue. But if it doesn't decay to 0 at the end of the block, you need to use the force exponential window, which is a popular way to do. But that introduces extra damping to your final result. You may need to take into account that. And all different windows, but more popular will be the force exponential window will be used for hammer impact test. But for my case, I tune, since I'm using a plexiglass plate, it's pretty high damping, so it decays very fast. So that won't be my issue, so I can use uniform window. And typically, you use linear average to several impact. And for this demonstration purpose, I use 4. But if you want to average more numbers to get a clean, nice, accurate result, you can increase the number to 6 or even more. But that takes time proportionally. And besides that, I think that the others, yeah, just self-explain to themselves. So I'm not going to go over these. Let's go back to this input channel setup. And compared to the other general tests, we have this DOF, which consists of the point ID and the coordinate directions. So let's say I'm exciting at point 29, positive Z direction. So you can all choose that. And you can see we support all 3 coordinate systems. So you can choose X, Y, Z, or you can choose the, all the different angular locations. It depends on your structure, how you build your structure. So you should follow that and without making mistakes. And let me just set back to 1 and 2. So my response channel will be channel 2 and channel 3. So I'm going to start with channel 1, I'm sorry, point 1 and point 2. They all go to Z direction. Remember, I'm dealing with a simple plate. So, and for point increment, I set up to 2. So once I click next point, it will increment by 2. So 1, 2, and then it will move on to 3 and 4, and so on and so forth. So by going all through like 20 times, you can finish like a 40-point measurement. And of course, the input mode, I'm using ICP sensors, and IEPE should be turned on. So that's the input channel setup. So not too much to talk about, but keep in mind the DOF setting is crucial. And every FIF measured associated with the channel will have a label for that DOF, and that associates the measurement to your geometry. Okay, move on to right. We have driving point selection. And driving point is such that the response and the excitation at the same DOF, meaning the same point and same direction. The purpose of that is to help people, or to help the testing people to decide where to drive the structure. If you are fixing the hammer, where's your hammer excitation point? If you're using a model shaker, where's you put your drive locations. And the idea is that you survey multiple possible good locations. Because for model testing, people all know we have the node points, and it depends on your structure, you have node lines. So you don't want to use these locations for your fixed driving point or fixed reference point of response if you are roving hammer. So for that purpose, you can survey multiple locations, and then you can pick a location which has the FIF shows, or say illustrates all the resonance peaks. And between these resonance peaks, you see an obvious valley. So for that FIF, for that location, it can be a good candidate for driving point. I'm not going to go through this testing, but just to talk about this feature so you can use it. And all the testing data is kept to this tab only. So it will be labeled, clearly labeled as a temp FIF or say temp H. So it will be separate from the real testing. Even here, if you say driving point setup, you set up to different locations, it would not change the input channel point and direction settings. But this is like kept to this tab itself. But the purpose is to help you decide to choose the right driving point. Okay, so with that, let's move on to the measurement. So here we have this measurement tab, and this is where you do carry out the model testing, and all the control panels will be in effect. And let's look at that. So here the setup, as you all know, you can customize the display. You can add different types of signals from different channels, and you can have multiple windows, and each window can contain one or multiple signals. So it's totally customizable. But we have one unique one we call the acquisition status. So here it just indicates, say, how many points you're going to measure. For my structure, I have 45 points. So since I haven't started tests, I did a couple of tests like yesterday. So it says 0.1, 0.2 is acquired. And 0.3, 0.4, it tried to do something, but the others just say no required. If I start one, it will say in process. So we will see that kind of behavior. And also, many times you say, I did a test and I checked the data, I found the issue, so you can repeat. So no problem. You can set back to redo this test, and the software is designed such that it always takes the newest measurement. So if you do 0.1, 0.2 again, the newer one will be selected for the model testing, model analysis purpose, and be added to this model data selection tab. I will discuss that a bit later. So here, this helps you to indicate where you are and how long to go for this model testing to acquire the FIF signals. So for the hammer impact test, my preference is, say, I put up the channel 1 time block data to just check the inputs, the hammer excitation force, and I can check also the response. And I can undo that. And of course, I will look at the coherence, because that's a good indicator whether these several average or say several impacts, they are good enough. And then the transfer functions, or say frequency response functions. For this case, I have H21, H31, and the channel will be changing accordingly based on where I am. So that's the layout I prefer, and you can set up the way you want, and no problem. And it's fully customizable. And another thing we need to talk is the trigger. So let's look at the setup trigger quickly. So for hammer impact test, and typically you can say we want the input channel trigger, and so we can do the manual arm or auto arm triggering. So let's look at the trigger settings. So I'm connecting to the hardware, and so typically we can do manual arm or auto arm for hammer impact test. And free run means without triggers, so once you say start, it will start acquire data and quickly go through the average. So it's not useful for this case. And so let's stick with the manual arm, and we can specify a certain number of points delay. And for this case, we specify negative delay for 100 points out of 2,000 points, so about 5% delay, negative delay. The idea is to include the whole impact, even just a little bit ahead of the triggering point. The input channel trigger level can be just specified. You can enter the value, how many pound force or how many newtons, depends on your unit selection. Or you can just drag this level up and down, so graphically. So it's very, very easy to set up these. So you say 1, I want a nice even value. And also at this moment, you can hit your hammer, and you can see the live response, and you can check if I hit right. So with this level, for this hitting level, you can see 1 pound force could be a good candidate, good setup. So if we're happy, and then we say, okay, we take that settings, and now we are ready to go. Here, you will see some more buttons compared to before. The roving setup, it's you already did that, so some people just say, why you have that again? But here it helps you to check, say, okay, you are roving your response, and you're fixing the, I'm sorry, okay, for my test, I'm fixing the excitation and roving the response. That's true, so increments 2, so you can just check everything's good. And if you want to change, you can change it here, or you can change it at the setup test configuration panel. Okay, and then you will see here next point and the previous point. At this moment, they are grayed out since we haven't started the test. If you start the test, you finish one point, say, for 4 impacts, and these two will become available. And typically, people want to start with 0.1, so you can always increment the point number, so you can see next point. If you are going down, that still you can do it. And also, some people will say, what if I cannot finish the whole point in one test run? That's fine. You can have multiple runs. The data will also be managed to be added on as you carry out the test. Run 1, run 2, run 3. They will all, if you go through the points, they all will be added to this model data selection tab, which will going to be ready for model analysis purpose. So even one run or multiple runs doesn't matter. So the data will be managed for you by this software. Okay, so now let's start the test. And don't forget to make sure the trigger switch is on, because we're set to manual trigger. If you don't turn it on, it just behaves like free run. So, okay, so we click run, and it will pop up this waiting for trigger window. That's as expected because it's manual ARM trigger. And another good feature I want to show you is this window is resizable. You can make it bigger. Once you make the window bigger, the font size also goes bigger. Sometimes you are kind of like away from your computer screen, and you can make it bigger so you can look clearly. But if you're sitting close, you can have it, and you can see the other part of the display. And of course, if you have multiple screens, you can drag it to the second screen, so you can have more viewing space. So let me just put to here in the center. So now I'm going to hit my hammer. I'm going to pick some point. So this trigger preview window shows you the impact force and also the response. And for response, I can check both response channels. For this case, I have 2 transducers, accelerometer. So I'm measuring channel 2 and channel 3. So, and I can zoom in, zoom out to check, and also the response. As I mentioned, like for the response with hammer impact test, you want the response to decay enough. So for this is pretty high damping structure, so that would not be the issue. So with this 2K block size, it just decays to 0. I still pick this big block size just for the frequency resolution purpose. I want some very high frequency resolution. And I can also unzoom that. So you can see that's being enhanced from the previous trigger preview window. Before we only say preview the fourth channel, and you cannot zoom in, zoom out. And we look at that. If it's a good one, we say we accept, and then we move on to the next. So I will hit that place again. And I think you can notice I double hit it. And you can see here the red, the font in red just says double hit detected. Remember I checked the double hit detection enabled, but I didn't check auto rejection. If I check auto rejection, it will just flash this double hit detected and then automatically reject it, just like a reject, and it asks me to do it again. So that's double hit detection in function. So now I have a good hit, so I can accept, and the next. So I will just finish this one point just to show you the operation process. So accept. So now I have 4 frames be acquired. And here it indicates 4 out of 4. The first 4 is accepted. The 4 is required. So 4 average out of 4, so acquired. So we've done this point. And now we see next point and the previous point be available. So, and here we can see the point 1, point 2 now becomes from yellow to green, which says in progress into acquired. And now if we say next point, And you can see the waiting for trigger window. It changes, just say waiting for trigger, and it indicates you the excitation. Still, you fix it at 29 positive Z direction, and response is move on to the 0.3 and 0.4. And here on this acquisition status, we indicate in progress for channel 3 and channel 4. And some people may use triaxial. For that case, for every point, you will have, say, 0.1Z, 0.1X, 0.1Y, depends on your setup. So you can use 3 channels to come as the triaxials. So channel 2, 3, 4, and they're all measuring 0.1. And then the second one, so you need a large channel count system, basically, if you're dealing with this, like, large structure has more points, and you have more transducers. So still you finish that, but you can do a triaxial way. So a majority case, people say for plate, you measure the Z direction. That's a significant response of the vibration plate. The X, Y are very limited, so it's fine if you don't measure them. But in case you measure, you will have the 3 items. So 1X, 1Y, 1Z versus 29 will be limited. So the software just handles uniaxial or triaxial transducer for any kind of combination. Oh, I kind of like forget to mention. So here is the coherence, and we see I didn't hit very carefully, so it's not that a very nice one, but just it illustrated. You can look at that, you can redo it, so because there's some issues. But here, this is one, and so here, this is the testing process. So until this moment, we've done the FIF data acquisition. And I'm going to switch the test. I will stop this one. I'm going to switch to the MIMO FIF, which typically used for model shaker testing. I will go through some unique features of that, and then I will bring in a set of pre-acquired FIF data and go through, talk about the model analysis process. Okay, so let me switch to another test. And typically, we all know with hammer impact test, the test setup is quick and easy, and it doesn't require the model shaker. The setup is much faster. But for some many structures, people say, let's use model shaker. And with the large channel count dynamic signal analyzer, and with multiple transducers, so it's more efficient and, to finish the whole test, because you can have a 32-channel analyzer, and you can have 31 accelerometer, 1/4 sensor, so you can get 31 transfer function in one shot. And another good feature of this MIMO FIF is you can choose different waveforms to excite your model shaker. And typically, let me look at this. So the very common waveform for drive the model shaker, they are like a white noise, and people also call it random, which is a Gaussian random. So that's a very popular waveform to drive the model shaker. This is a broadband excitation, and because of the leakage issue, you would use some hanging windows to dealing with this random vibe excitation. And based on the random, we also have a burst random. So burst random, the idea is we have this random excitation within a block, a certain percentage, let's say 60%, and then the next 40% we don't output anything, so the excitation will be 0. And under this excitation, you can see the response will be excited, kind of like transient response, and then as the excitation goes out, the response will decay. So you will tune the burst random percentage, to allow the time for the response to decay. Just very similar to to the hammer impact test. You can tune the block size to have the response to decay to 0. If this is achieved, you can just use the uniform window. You don't need to use the hanging window. So that's why burst random is very popular for people doing model shaker testing. And besides that, there's two types of the theoretical random excitation, the pseudo-random and theoretical random. So let me just turn on the pseudo-random with the IMS value. That's a voltage setup. And we can look at here. So we will see two setup parameters, which are the extra. So the number of delay and number of cyclic. Let me explain this a little bit, what they are. And for the pseudo-random, and it has a unique, or say, constant level for every frequency lines. But for the phase, it will be randomized. So once it generates one block of this pseudo-random, it will keep it, use it multiple times. For this case, it will output 3 blocks with this exactly same block of pseudo-random 3 times. And there will be no measurement of the data. So that's why it's called delay blocks. So the idea is to excite the structure and bring it into steady state response, so which the response will become theoretical. So that's the whole idea. And after that, we are going to measure 4 blocks again with the same pseudo-random block we created. So this same block will be repeated by 3 plus 4 times. And with this 4 cyclic block, we will take 4 blocks of the time response to the time domain average, because the response are theoretical. So we can cancel out some random noise and then keep this theoretical information in there. So that's the beauty of this pseudo-random, and the same situation for theoretical random. But you can see on top of this 16 spectral average, we also would have this 3 plus 4 blocks. So the total block will be 16 by 7 for 1 point. So you increase the testing time dramatically, but you end up with a much better result because of this whole process of delay and time domain average. So you spend some time and effort, you get much better results. So that's why people have this pseudo-random and theoretical random. And now let's look at theoretical random. And what's the difference is it's still like very similar to pseudo-random. From one block to the next, the phase are randomized for every frequency point. And also the level for each point can be randomized. For my case, I set up to 30 or 40%, and I can set up the level. So this is a constant level. But for every frequency point, when I say create a new theoretical random block, the level will also be randomized from one line to the next. So by just changing that, so it's totally randomized the amplitude and the phase for each frequency point. So I can achieve much better, and in model testing, people also always call it, because the structure always has some nonlinearity. But what's measured FIF is called a linear estimation. So by using this theoretical random, change also the level, not only the phase, you can get a much better linear estimation of the FIF. So that's the purpose. But still the same, you need to go through this number of delay block and number of cyclic, or say, time average blocks. So the testing time will be increased dramatically. So that's the reason still like a burst random will be more popular being used rather than clean to that. But for some situations, you want a very nice clean result, you can go to this pseudo-random or theoretical random. And for the MIMO case, I would suggest you to always use theoretical random over pseudo-random, because you want to randomize the level, or say the excitation level also, not only the phase, because that will help for the decoupling of this driving matrix. You have multiple drives, or say multiple reference. Okay, so that's enough for the testing part and the since time, and let's just move on to the model analysis. Okay, so let's assume we finished the testing. So we have this model data selection tab filled up with all the necessary frequency response functions. For my case, I have 0.1 to 0.45, so 45 FRF. And this is a shaker test, so I fixed the excitation at 29, so they're all 29Z. And I can check this FRF one by one. You can use the arrow key to quickly go through. Or once you say display select signal only, you uncheck that, you can have multiple FRF be select to be checked. And also you can change the format. You can say, you can check magnitude phase or log mag phase, or you can check real imaginary. And many times the imaginary part, if you are measuring acceleration versus driving force, you can look at the imaginary part, which the peaks indicates kind of like the mode shifts. If you have a simple beam, or you can just imagine how the mode shift is going to be. And all the supported features are there. So this is the model data selection. And here it also works with the geometry model, and we can turn this surface on. And when you select different FRF, it just indicates which points being selected. So you can see the red dot just moves around as I click randomly to any different signals. Okay, so if we look at the data and everything's fine, and we can move on to start the model testing. So the button is you right mouse click in this window anywhere, and it's a model parameters. So that will bring into the band selection tab, and you can select the band. Let's do that. And so here, that's the band selection. Here, we just take use of the MIF functions, and the default, or say the first MIF is called the multivariate MIF. So we choose that. Based on the nature of this MIF, the drops close to 0, that indicates where your resonance frequencies are. So this is the only one which has the drop and indicates the resonance peak. For all the others, like the complex MIF, we also have that. So that's like the peak will indicate where the resonance frequencies are. So, and also you can use the imaginary sum. And the imaginary sum, and we always have the sum of the FRFs just shows underneath, but you can turn it on, you can turn it off. So, and you can see the imaginary sum, it looks similar to that, but they are different. So because this is only the sum of the imaginary part, and that can be a good serve for the MIF as MIF function. Let me set back to multivariate, and I can set the cursor. You can do, say, I want to cut into this range, or I want to cut into a small range. You can select it. And we're going to use the stability diagram, which is for the single reference, the curve fitting method we use is called the least square complex exponential, the LSCE, which is a time domain curve fitting method. This is a very, very popular and proven to be working one. So we implement that one for the single reference case. So let's select this band, and let's select how many modes we want to interpret this result. Say 24 for this case. I know we have like about 5 modes, and we can say calculate stability. So now it brings into this stability stage. On the stability, you can see, so always is like a red circle, and also we see some like a blue, the green cross. They indicate the poles, but they are different poles. And here we say the red circle, that indicates a new pole, which could be any type, which could be the system pole or could be the mathematical pole, because we force it to go from number 1 to 24. So we say, give me 24 poles. So it's just do the iteration and identify all these. And in the meantime, we will compare the poles from one iteration to the next. If the pole, the natural frequency and damping, they are not changing, it will be labeled with the green cross. We call it stable pole. So here we see a line of stable poles. So that's a good pole, or say a mode can be selected. And here we have the second one and the fourth one, I'm sorry, third one and fourth one, and then the fifth one. And in between the red one, we can omit that. These are all the mathematical proof. If we put the cursor on here, you can see if we put the mouse onto any this button, at the bottom you can see this is at rank 19, so the 19th pool, and the frequency damping. And for damping for this one is 8%, which is super high. And if I move to another one, and I believe there's some, the damping will be super high. So we know these are not the good ones. And like this, and I think for this one, the damping is 17.5%. So these are just the mathematical proofs. They are not stable either. So we are not interested in that. So once we look at that, so we can just pick. So you just use your mouse, click, and you can pick that. You will say which one to pick. Actually, it doesn't matter because they are stable. So the difference between these green cross poles, they are very, very small, smaller than the criteria we set to do, let's say, like a 0.5% or even less. So you can just select these. And once you select, it's added the pole to the list. You can deselect that. And once you're ready, you can say calculate modes. So typically, the modal analysis has been carried out in two steps. The first step, identify the poles, use the LSCE method to locate or say to find the natural frequency and the damping coefficient. Once this is done, this will be used to calculate the mode shift. Mode shift will be calculated from the residual value from the FIF equation. So we can calculate the equation, and then we just say, okay, we give a name, and then I already have one calculated, so I don't need to repeat. So now then it brings you into the next stage called animation. And this animation is just a mode shift animation. So later on we will discuss the ODS animation. So here, this is the animation tab. So the left side, it indicates the shift information. So we have a shift table called 5 modes saved, and it has 5 modes. This is the MAC table. So it indicates the mode 1 to itself, and you can see mode 1 to mode 1 is 100%, and then to the others, they are very low. And we can also click display MAC chart. So this indicates the MAC functions. So from mode 1 to 1, it's 1. Mode 2 to itself, it's 1. But across these different modes, they are very low. And here we see some couplings from mode 4 and mode 5. So we need to take some time to check what's going on there. But the first 3 modes, they're all well separated and identified. So that. And if you have multiple mode shift tables, you can do the CrossMap analysis. So that will be, you can select another one. I'm sorry, I have to close that. And you can do the CrossMap. For this case, so far I have one, but I need to have another one. You can also import a mode shift table from other tests. You can do the CrossMap analysis if you want. And now let's look at the animation a bit. So if we just click, say, mode 1, so you can see on the geometry window, just like it's forming. And you can see this is the first bending, so it's very clear, and you will see 2 node lines. And the animation amplitude can be adjusted to be high or low, so you can just adjust it. So if I want to exaggerate the deformation, we can do that, but that could be too much, so I make it. And you can also increase the speed to make it much faster or make it slow. So you can adjust all these. You can remove the points. And here I have the contour display turned on, so it uses the colorful, say, to indicate. Now I turn it off, so it's totally green, but the structure still deforms. So I can turn the contour on. So the red indicates the full deformation. Blue is kind of in the middle, and green is kind of, this is the node line, I would say. And we can show it in this quad view display. So from the top, from the side, sorry, and we can see obviously this is the first bending of this plate. And for the second one, this is the torsion. So we have the node line, and in the middle, X and Y direction. And I can do one frame step. So I click it, and then I say next point, next frame. So I can mouse click, so I can do the animation. These are just the standard features of any kind of like a model analysis process. And we can see obviously the node lines just cross that. And the third mode, which is a high order of this torsion. So I uncheck that, so I can go back to this animation continuously. And of course, you can turn on the points, you can turn on these angles, you can turn on the lines, you can turn on the node. So it's getting very, very busy here. And you can see the node direction of this surface is just changing as the animation goes on. Here shows the MAC matrix. Here just shows the list of the modes, meaning frequency and damping, or say natural frequency and damping coefficient. And once you select the mode 3, the mode 3 mode shift data will be displayed at this region, say the DOF and mag and the phase. So that's the mode shift data, the magnitude and the phase. So that's for 45 points. Okay, so that's for the model data identification and the animation. In between, we also discussed the MAC chart, or say calculate MAC matrix. The next is the FIF synthesis. So when you do the curve fitting, you get the data from like a FIF, the measured FIF signal into these separated or say decoupled modes. Each mode consists of the natural frequency damping and the mode shift. Once you have these modes identified, you can put it back together to reconstruct your frequency response function. So that's called synthesized FIF. So what we can do, we can just say check the synthesized FIF against the measured one. So the green one, maybe the line is too thin, you may not see it clearly. The green one is the measured one, and the blue one is the synthesized one. So we can see a good match of the synthesized versus the measured one. And we can go through from different points of these FIF signals. And underneath we have a run button, and we can say have a speed. So it will just go through this one FIF to the next. So if I click run, so it will automatically going through this. So I just sit back and watch it. So every 2 seconds, it will just show me one FIF. And it indicates now at, say, the measuring point 11 and now 12 versus the excitation. So, and we can do that. And you can change the speed, say, to be 1 second, so it goes much quicker. So you can go through that. So here is just a way to verify your identification results, whether it's right or wrong. And let's stop this, and let's move on to look at the last tab, which is called the ODS. And the ODS stands for Operation Deflection Shift. So the idea is it take a set of testing data and do the animation on the geometry. And the data can be time domain or frequency domain. So for this case, I have a set of shaker testing data. So with the model shaker, the excitation force can be controlled. So the response level is also kind of like relatively scaled. So it would make sense to do this time domain animation, or say ODS analysis. And another way is if you have recorded data, we also support that. You can bring in this recorded data with every point and direction labeled, so it will associate to your geometry and do the time domain animation. So that's like a real-time deformation analysis. So if we click start, and we will see this, the structure starts to move and based on the level. So initially it's built up. So you can drag this to any locations, and you can quickly drag it. So once you release it, it just goes. So you can see how the structure deforms. And you can pause it, or you can do it step by step. So it's a point to next, so just doing that. So this is the time domain, and we can also look at the frequency domain. So for this case, we suppose this like the FRF. And so let's just drag it to here and like at this point. So if you look at structure, this is more like this structure rotates along the x-axis. So this is one rigid body mode at low frequency. And I believe I can find maybe this is another rotation along the y-axis. And let me see if I can find the translation. Maybe not. They're very close. Not enough point. But anyway, we are not interested in the rigid body modes. We only care about the flexible modes for model analysis. So for this case, we have this. And we can just keep going. So, and you can see it's corresponding to these. So let me just do this quick go. I think I have one data just kind of out of the range a little bit. I need to double check. So that's the ODS. And so you can see that kind of like conclude this, the whole testing. And you can see the best benefit is the testing and analysis. It's whole software in one. You don't need to stop and export the data and then import to another software just to do it again. Okay, so I think I will conclude this session, the introduction session, and we can go into the question and answer. So, and yeah, any questions?
I see there was a question in the chat here. Somebody had asked if there were any solutions on OMA or operational modal analysis.
Oh, I see one, and I see a couple of. Okay. For the OMA, the operational model analysis, it's our developing plan. I think in later this year, probably we can release it. So that's the status. And let me see, I see more questions here. So, okay. So one question is, can I calculate MAC matrix for two sets of modes coming from test 1 and test 2? The answer is yes. So you can bring in a mode shift table from other tests and then do the CrossMap analysis. But also within one test, you can say you do the curve fitting to get one set, and you can do the next. You can say maybe you change some setup a little bit, different band widths, more to the left, more to the right, and you can say identify, and you can compare. So all these are all available. And even we can import like a mode shift from the third part. If you have like a UFF mode shift data, we allow you to import that.
Did you know that there was hockey here?
Can you speak up a bit? I can barely hear you. Okay. Any more questions?
All right. Well, if there are no more questions, then we will be in contact with each of our reps and distributors to kind of discuss the marketing and discuss the price list and everything. This software here is meant to kind of start putting Crystal Instruments on the map of this complete solution here, kind of on the level of B&K and LMS there. So that might give you a little perspective on what this is and what this can do now. So I want to thank everybody for all their time that they took out of their day to see this presentation. We're very excited about this. We really think that there's a very large potential here. Anyway, thank you guys very much, and we will be in contact in the very near future.
Okay, thanks, gentlemen, for your time.